Hello ladies and gentlemen, my name is Jan. Welcome to another video on this channel covering the subject of the Minuteman machine and how to 3D print a Benchy in less than a minute. The last video did end with footage of me printing a 1 minute 59 Benchy, and a lot has happened since. So in this 11th episode, we're gonna talk about three things mainly. We're gonna start off with something everyone wanted to see according to the comments. We're gonna have a real proper high-speed camera pointed at all the parts of the motion system. This is possible because one of the members on my Discord, namely Emma, supported this project with a Chronos action camera and her knowledge in taking the footage of it. In the second part, we're gonna address all the short-term solutions we can derive from that footage. You will see me going all on the nitty-gritty details about each and every of those systems, and we're gonna overlay it with what we actually captured on the camera. And in the third part, we're gonna actually do some printing. So my plan for now is to go with the same G-code of 1 minute 59 and see what actual kind of a difference we can make with all those little solutions. So let's start with this incredible footage of the high-speed camera. da da da, da 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 da, da 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 da. So what gets me the most about this awesome footage is just how deep you can have a look in a strange world that is a complete secret to the naked eye. We can learn a lot from that. There is going to be short-term solutions, which I'll put on the machine now and going to take you with on the tour. And then there are long-term solutions. And that's why I invite you to leave everything down in the comment section, what you can read off that footage. And also, again, there is a link to my Discord with a very friendly and knowledgeable community that has developed there. And I thank all of you people contributing to the project over there. All those long-term solutions will be used in the next iterations, but for now, we're going to learn more from that and then derive that into the next full-blown iteration where we try to tackle the 1-minute goal. So starting off, we're going to deploy a new kind or the next iteration of the motion platform. And the most essential part will be about stability. This process will add a few grams, but I think this is well spent. And since we got a bit of headroom left in those motors, I think we can justify that. And as you can see in those clips, I'm gonna get rid of those. And in this next iteration, we're just gonna put them in here and attach them with some grub screws. So we get rid of that big, it's like 3 grams or something. But this mass is kind of a reason why this is being excited so much, I guess. And then also we're gonna focus on what was happening there. In this footage, you can see how much the whole Benchy is shaking. And while that may have several reasons, I think most of it is because this platform is shaky. This can't handle all the accelerations, especially with the added weight of the Benchy on top. I don't think it is the tipping of this piece because it's like surrounded by that glass plate on top. As you can see here, there's a big cutout. And while it would be best in terms of performance to build that out of carbon fiber, I think that's out of range for now for complexity's sake. It's a nightmare to prototype with, but I think I'm going to do a very lightweight solution out of aluminum, which will do a next iteration print bed. I'm going to turn that on the lathe and then we'll glue it into here, and that will make up for a much more stable print bed, which is also not prone to warping, etc. Last but not least, I did this reinforcement again in here. I hope that will get rid of that scratching sound. For a first step, let us go ahead, lap this in on the height that is determined by the rest of the parts here. Let's turn this part and glue it into here. Let's attach the cables again and then focus on next things to improve. So I've chucked up this 7075 grade aluminum in the lathe, and we're gonna turn something like this, which will become the print bed again. Hopefully in a very good configuration of stiffness and lightweightness. So let me turn that. Well now, and after parting it off, I put it on the other lathe, and we're just gonna do facing of the backside and then hollow out as much material as possible to make it as lightweight as possible. Well yeah, and also try not to break it in the process. Alright, update time. So this is the old motion platform, air bearing, whatever you want to call it, that has been on the machine for the latest episodes. This has been weighing in at around 84 grams. And this is the new one, which I did the lapping on. It has all the screws in here, and this is the plug you saw me turning, which will be our print bed. This is as thin as I dare to do. This fits snugly in here, which will be super glued in here. Super glued because this print didn't turn out the very best in terms of geometrical dimensions. I had to lap not just this, but also these parts because it hasn't been going flat and parallel before cleaning up. Both of these parts weigh in at around 107. So basically a 22 gram increase to the previous one. But I think in terms of bending stability, this will be a lot better because this is one integer part. So with the old version, all that tipping was coming down to this single point, 20 millimeters, where it has just been locked on by a single screw. And this, on the other hand, is resting on a way bigger radii and is a single integer piece. So I think this will give us plenty more stability. Adding 20 grams to the mix with the headroom we're having on the machine right now should at least be beneficial in terms of the print quality. At least I hope so, and we'll find out soon. So as I said, I've lapped these again to match this new part. I had to take off like 1/1500th of a millimeter. Again, we're getting rid of those tensioning devices. I'm gonna put those cable on in these lines which intersect at the angle the motors are coming from, and then we're gonna just lock it with the scrub screw. While we're at it, I think it's a very good time to talk about the material I've been using here. So basically this is a PLA, but then basically it is not. I'm not affiliated by those guys, but I think it's worth a mention. This material comes from the Austrian company Extruder, and I've been using that for all of my prototyping work for the last couple of years. This is the stack of material that I printed as prototypes for the machine. This material is basically PLA blend with carbon fiber added to it. And this is one of the stiffest materials I have ever encountered in 3D printing, and I've messed around with nylon and PP and ASA and whatnot. This has been my go-to solution for most of my 3D printing because it's very stiff, it's UV resistant, it takes temperature up to 100 degrees, give or take. And also it's quite affordable, and the very best thing, it's really easy to print. So basically you never get failed prints because of warping or such things. It basically prints like in PLA. Alright, addressing the cooling situation. So these are the two prototypes I've ran on the machine up to now. This one has been very close to the nozzle, let's say 5 millimeters apart. And this is the one with the shortened needle valves, and these are like 5 to 6 millimeters shorter. And if you have a look at this footage, you can clearly see what the effect of those high currents in terms of air volume actually do. So with the Benchy, this is just one of the examples here, it has been facing like this and the stream has hit it on this front side. And what you can basically see in those high-speed footage is that the material here is really blown away and has no chance of solidifying where it is supposed to be. And that's why most of the Benchys are looking worse on the side where the air stream is coming from and better on the back. This isn't the best example, but trust me, it is like in all of that. But I've also found that having more stream of air is beneficial for the print itself as a whole. We need a lot of cooling air in order to do so. So before we go ahead and I show you what I've planned next in terms of cooling, we're gonna do just a shot in the dark with some surrounding airflow, which is also something a lot of guys pointed out in the comments. And this is basically going to be a combination of both of these. And then I'm gonna set them in here, basically one by one. There will be a total of 12 in here, I guess. And it's gonna be 6 long and 6 short ones to have a very focused point in the middle that is being cooled and also get some more air to the surrounding parts. So let me do that. Alright, next up in line, as you can see, this is the old trusty heat sock I SLA printed on here to give the nozzle a fighting chance of keeping its temperature while the air blows on it. We're gonna get rid of that, install a new nozzle. This time I'm opting for a 0.4 millimeter because I think our main issue right now is the cooling situation, and extruding just 1/10 of a millimeter more is a lot if you consider the volumetric of it. And I think we're having a way better time cooling this 0.4 millimeter stream of extrusion rather than the 0.5, and we have to make up for that in terms of speed and accelerations. And this is going to be replaced by something that has also been SLA printed, and this is a pretty good time to introduce today's sponsor of this video, which is PCBWay. This is the part that is going on there, replacing the sock. This is also being SLA printed in a material that resembles ceramics. According to their website, this is around 350 degrees centigrade worth of holding up. And as you can see, it covers way more of that lower heating block, and it's going to be, again, secured by wire. While we're at it, these are the other parts I had in just one single order of them. This is polyjet printed nylon. This is a sheet metal part. Yeah, you can have a wild guess what this is for. Then I had in the same order some SLM printed aluminum. This is going to be the replacement if I ever encounter like the hard limits of the polyjetted ones that are on the machine right now. In case those break, I have this as an upgrade. And this is a very special part for a different project. This is one piece printed in stainless steel. The sheer variety, what you can have there on their website, is just mind-boggling. And when it comes to how easy is it actually to get something from their website, you just upload your step files, your STL files, whatever, you select the desired material, the desired quantity, and you get an instant quote. And after that, the quote is being like redefined by an engineer of theirs, and they're gonna come up with solid questions on maybe you think about wall thicknesses, etc. And the pricing is just phenomenal. Parts were shipped in a matter of 8 or 9 days, which is awesome for this variety of materials, and then shipped to Germany. A huge thanks and shout out to PCBWay for making all of this here possible. And we're going to see a lot of those parts on the machine very, very soon. Speaking of which, I think I just finished putting it all together again. So let's have a look together. And this is how it looks right now. You can see the glass plate isn't on here. This is the last step. Cables are actually now put into there. As I said, there's the grub screw, and they just follow in on that angle here. And this is making up for a lot of slack in the system earlier on. So I guess a lot of that elasticity we've seen in the slow motion footage has been taken right out of the equation there. And also any mass added to this long string will not help with any resonances. And while these little pieces are only a few grams, you can see that those are wiggling around like crazy. And I think shaping off any weight here is essential. And again, it takes elasticity out of the system because everything will bend. Everything's made out of rubber in our world. And then, as you can see, one of the bigger changes is this omnidirectional cooling. So for a long time, I haven't done this because most people that have been doing research for cooling found out that if you blow from all directions, the air basically doesn't have a way to go. And what I was trying in earlier attempts was to have this laminar sheet of flow that is like going across our Benchy in this case. But then when Emma was here and we're talking back and forth about small niche solutions, she pointed out that having a laminar flow on the part isn't actually beneficial, and that makes total sense. So during the last attempts, the Benchy always has been in this position and the air was coming from this side. And what ends up happening is that you mostly get the laminar flow I was talking about from this side. But you will have turbulent flow on the opposing side no matter what. So you basically have two conditions on the sides of the Benchy, and we should try to make it more evenly distributed. In this case, since I'm using these needles, there is a whole lot of space here where the air can freely leave the area surrounding the print. So this is what it looks like from below. Last but not least, you saw the footage of the springs. If just one axis is moving, the springs, they don't change in length. The length change is just if the other axis is moving as well to make up for that amount cable has to stretch. This is not much, but you have seen how much resonance there was inside that spring, how it was bouncing back and forth. So again, for a very short-term solution, I put in some foam, which should act as a dampener. Let's see how that works. With this camera I can do 1000 FPS as well. Maybe we can get a glimpse of how it compares to the real slow motion shot. And we'll see if that is killing the internal resonances of the spring. It can still do all the stretching, etc. So these were all the short-term solutions we could find from just having a look at the high-speed footage and just adapting to it for now. All the other information will be used on later iterations, but now let's see how it compares to before. I tried to do a run with the exact same G-code to compare it to the actual world record run, and we have to address that later on as well. Then we're gonna do some tweaking on the G-code itself and try to improve there. So this is like my schedule for tomorrow. Let's see how that works. So I had a thought in my mind and I was trying out a thing to find a value set for the pressure advance settings. And what you can see here is a small LED, and I can ping this on by giving it a code line in the Clipper software. And what I essentially tried to do is I had a G-code that would extrude some material, and right before that set this LED to the high state, and then I'm gonna extrude, turn off the LED and wait for some seconds, and then just and what I tried to find out is if I can get very close in terms of those values in pressure advance, then by having a look at high-speed footage. So I recorded this on the camera with 1000 frames. I'll put the original video here. So basically, as you can see, the LED turns on and immediately after the filament is coming out of the nozzle, and I wanted to visually check what the delay between those is and maybe find a range of parameters that were applicable to the pressure advance measurement. When the LED starts, it takes about 6 frames in this 30 FPS footage, basically extrudes some material, and this boils down to 0.2 seconds roughly. But that is a value I have used before for pressure advance, and in practical applications this wasn't really the case. So what I guess happens is that there is also some kind of a delay on these commands inside the software. So I guess I have to go back to manual checking the pressure advance values. This was just an idea I had to see if we can check that, and if anyone has an idea on how to actually measure those delays coming from the code setting the LED high and the LED actually turning on. If someone has an idea how to measure that, maybe this would be a very good starting point for doing pressure advance fine-tuning for different materials. So, but yeah, let's do something else now. So I've been doing some testing yesterday, and it wasn't really like fitting to get the camera in there, but I made a few snippets that I will put at the appropriate time. But have a look and let me give you an update. So this is what I printed yesterday, and as you can see, let's start with this one. This is number 31 in the total prints this machine has done so far. So what has happened since? These are all the changes I've made and also documented in the video, like we put some dampening in the springs, we put in a different type of air bearing, changed it to the aluminum printing bed, we have the 360-degree cooling nozzle installed, and also started using the 0.4mm nozzle and put in the different heat sock. So print 31 was done at 210 degree, it was facing northeast just like the others before, and I used mediocre cooling on that. And basically if I take the former, let's call it the world record slice of 1 minute 59 at a 0.4mm nozzle, that comes down to 2 minute 19ths, and I ran the whole G-code at 50%, this comes down to 3 minutes and 20. And this is basically what I got out of it. So first of all, I'm pretty happy with that in general terms. As you can see, cooling has done a great deal of advancement over the laminar flow version we had before. Cooling from all sides seems to be a lot better in terms of not blowing the filament away. And the next print I've done, print 32, is basically the same G-code but has cooling cranked up to a solid 100% of what I can give it. And as you can see, all those areas up here with the pillars and overhang are a lot nicer. General cooling quality is a lot better compared to before. What I did notice, if you have a look in this direction, there are two things. So first of all, so these corners aren't 90 degrees, and also the whole part seems to be screwed basically. And what I found out after some investigation is that after I set up the air bearing, I had to do some tweaking on the parameters on the winch kinematic. It had like a scaling factor on the y-axis, and if you think about it, this was printed in this direction, so all the moves in the y-axis are elongated. It took me a bit to figure that out. Also prints 33 and 34 are like this, so keep that in mind. But the second thing I noticed was like this top part of the roof was like blown in. So that's why in print 33, I tried the same exact thing, but then when I came here to the top part, I turned the cooling a bit down just for this part, and this seemed to be helping quite a bit, but yeah, it's not perfect in that regard. Then with print 34, I finally changed those parameters of the screwage, and I think this is not perfect. I have to do some kind of calibration cube again to really measure those angles, but it's like I know where the problem is. And then with print 35, I changed the temperature and printed it at 5 degrees lower. This is 210, this is 25. This hasn't really done that much of a difference, and now comes the part of doing some fine-tuning, and this is where I'll introduce another way of calibrating the temperature, but let's not get ahead of ourselves. And yeah, for this video I try to get the quality of a 2-minute Benchy somewhere in a likable neighborhood. If it would look something like this, I would be pretty happy. I think I've just made up my mind that we try to do that with the 0.4mm nozzle for now. To go for a sub-minute run or something is kind of out of the question to do it with a 0.4mm nozzle. Only going from 0.4 to 0.5 adds 20 seconds to the print. So if we want to reach our final goal, I think the 0.5 or even above is the way to go. But for now, I want to try to focus on getting the quality right. And that's why we're going to stick with the 0.4 and again, try to fine-tune this setup here. So that's why I already went ahead and have put the accelerometer back on the machine. I just hot glued it on here. There were a lot of people commenting about the influence of that cable, but today I just don't have it in me to do the soldering job on this. We're just going to roll with it. This is by no means the last measurement of input shaping I'll do on here, but I want to confirm a few things. So we're going to do another set of measurements. Then again, we're going to have a look at temperature of the filament. There's a sophisticated way someone pointed out in the comments. We tried to follow that. And then finally do some runs on getting a value on the pressure advance and see where we do end up there. Also, I want to address something a lot of people pointed out in the comments. So the question is, does it make sense to start printing slow, dial everything in, and then go to a really high-speed setup? Well, I think the answer is kind of. I think you can dial your printer in and find stuff out a lot easier if everything moves slower. That's for sure. But what I found with these iterations on going really high speed, I don't agree with you. So if you have a look at this guy, this is 1 G code and ran 3 minutes 20. This has shaved off 1 minute by running it at 100%. This is 2 minutes 20. The difference is like 2 worlds. And I think if we go down into that kind of category, I think we have to tune our printers just for that exact parameter set. Thing here, or the big upside, is that your iteration steps are really, really small. Basically, every 2 minutes 20, I can get another data point. And with all the parameters we got, like temperature and pressure advance and speeds and feeds, it is pretty easy to set up a matrix where you find like the sweet spots of each of these individual topics and then combine everything. Alright, so after quite some fiddling, I finally got the input shaping measurement working again. And this time the results are way more like what I expected them to be. As you can see, I found the option on how to run those a lot higher in terms of their frequency. The last ones were like cut off at 130 Hz or something. This time I ran it all the way to 200. And as you can see, this is the y-axis graph, and it was somewhere in the 150 Hz range. There was a peak, but now we're at a way better like order of magnitude, and the results are pretty much what you expect to see. This is the graph for the x-axis, and also it seems to be climbing way here at the 200 Hz range, so maybe I'll have to extend that again. And then I reran the tests for the y-axis, but this time with the input shaping I previously determined active. So I found the option on how to do that, and what you can see here, this is one order of magnitude lower in terms of the response, and also at a very low response level or amplitude. And as you can see, this has gotten, I mean, not flat in a sense, but flatter-ish. When I reran this, all the resonances at 150 Hz, I could hear those by ear, were basically gone. So this is an interesting result, and let me just put that on the machine. Let us do some test printing to see how the ringing and etc. is developing. So right now I'm having a look at extruding temperatures, and as you can see on this tray, this is a test I conducted just now. There has been a guy called Steve Moore on the last video I posted suggesting a different way of setting the exact temperature on the extruder. For solving our cooling issue, to have the lowest amount of energy possible in the filament we extrude. This test has been conducted like this. As you can see here in the clipper, I continuously extruded some material at a set rate of 150 cubic millimeters. And that value corresponds to the volumetric flow rates of our Benchy, in this case the 2-minute 12 Benchy. This is 147 at best for the infill part. So, and I've been continuously extruding that material, and then I dropped temperatures down to the point that the extruder was skipping. And as you can see here, it got way lower than I thought it would. And this is with the cooling cranked to max volume. It did actually already do 175 degrees. There was the first skipped step of the extruders, but to like have a look at the absolute extremes and finding out what our best printing temperature is, we're gonna now conduct the test of running the Benchy at the lowest temperature, where the hot end can like melt the material as requested in the G-code. So I tried to run this again. This is at 178 degrees, and I'm gonna do some continuous extrusion. So as you can see, it does maintain the flow, but have a look at what happens . See the amount of oozing that's happening? It's really hard to film down there, but there is just the tiniest amount of material flowing after the extrusion has ended. So I guess maybe that could be the end of our little depositions here at those pillars. Let's see, I'm really curious on how this print will turn out. Alright, this is a very interesting result. This thing ran 3 minutes 20 with the exact same G-code, but with a new set of the input shaping and also at 180 degrees Celsius on both heat zones. And as you can see, in terms of cooling, this has made a tremendous effect on here. The whole outer shell is pretty much looking really good. As you can see, there's even the Benchy number plate visible at the back. So next up, we're gonna get rid, or we try to get rid of these small little knobs and blobs that it keeps carrying around between those pillars. So for the very first time, I'm gonna do some pressure advance. I'm just gonna do 0.05 on here. That seems to be like a standard value for direct driven hot ends, and we're just gonna see matrix wise if that makes any sense. We'll do 0.05, evaluate our results, and then maybe do 0.1 or 0.02 something to narrow it down and see it in real world applications. So let's do that. This is without pressure advance. This is with the value of 0.05. And I think if you have a look at these here, also here in the back, this has done some improvements. So let's go again with the value of 0.1. Let's see where we end up there. Interestingly, it keeps improving. 0, 0.05, 0.1. This is looking like a pretty damn fine Benchy. Let's do 0.15. So while the 0.1 value still had some stringing left, the 0.15 is almost stringing free and does not have these small little blobs. However, I now encounter some small, I don't know if it's under extrusion, I may put it on the scale in a minute, but at least these artifacts are now showing up. So what I can think of is, due to the nature of pressure advance, we do now have spikes in the extrusion G-code that are well beyond the 150 cubes I estimated, or which I set the temperature of the hot end to. I'm just gonna go up 5 degrees and see if that moves in the right direction. If that is not helping, I'm gonna see what the smoothing time has got of an influence on it and tune from there. So adding 5 degrees to the mix made our, like, let's call it under extrusion better. Yeah, but also we got a tiny amount of stringing back. And also I think the overhangs are looking a bit worse since the viscosity is different and maybe the cooling air is able to push that down more. So I think the sweet spot is somewhere between 0.1 and 0.15. So let's make that 0.125 or something. Dial the temperature back, or maybe let's meet in the middle there and go to 182. And let me think about what we're changing as well. Yeah, and I also changed up some speeds in the top fill as well as the bridging. And that added 4 seconds, so let's see what that kind of an influence has on the print quality. Yeah, usually print number 42 should have been the answer to everything, but in terms of fixing this issue up here, it is not. I guess print 39 with the pressure advance of 0.1 I like the most, and I think we're gonna dial it back to here. So start out with these values for pressure advance and leave it there for the time being. But what did actually make sort of a difference is dialing down the speeds of those overhangs and top fill. That is looking a lot better, and if you have a look here at the chimney part, this hasn't been able to close it fully. This hasn't done either, but it has done a way better job. We're gonna take what we learned from these here, make a combination of 39 and 42. And this time we're gonna run it at 75% speed override and then at 100%. And what I wanna show you here is that we can like dial in slow speeds to a reasonable good finish, and then once we crank up the speed overall, all the results from before are basically down the drain. I guess that's my prediction at least. Let's see if all the stuff we've developed so far actually make a real difference. So yeah, let's run 75% first. Well, I thought the difference would have been bigger, but yeah, that's a good thing for me. This one has been printed 30 seconds faster than this one, and you can see that pretty much here. The main difference is these overhangs. So let's do 100%. Alright, print 44 finished at 100% print speed of the G-code, and this was 2 minutes 20. Again, there is a bit of, I think, blowing the filament away down there. And then you can clearly see the limitations on the overhang part. But this was there again. And what I just have seen is that our 360-degree cooling nozzle was not 100% symmetrically installed, and it was like closer from this side. So this is the worst side. And now I fixed it, and I think it's now symmetrical. I don't want to push it. It has been running so freaking consistently. I didn't even had one single failure in this system today, and these motors are quite hot. So I don't want to risk breaking anything. But I think I will do one last with this issue being fixed, and also I'm going to turn down the cooling like a bit. I have the range from 0 to 2 bars, and I've been running it full blast for the last tests, but I think I'm gonna go down to 1.5 or something and see if we can improve our overhangs here or if it's getting worse. Yeah, also this is been estimated to 8.53 grams, and yeah, we don't have any signs of under extrusion. It's all there, but not yet at the right place. Alright, so 44, 45, this was at around 1.25 bars of cooling pressure, or well, yeah, or maybe 17 or 18 psi, foot, pound, square, inch, torques, whatever, for you Americans here. And I think this is not that much of a difference, but I just had a peek at the slow motion. I've took off those pillars, and I think there is no way we can like up our speed without having some kind of a paradigm shift in cooling those. So either we're gonna need some kind of a different cooling media or a different material or something. But I think in the final G-code I just have to slow that down here to get this quality right. But yeah, I think I'm gonna call it quits for today. I think I'm gonna set up a proper G-code to run a 1 minute 59. I think there's a lot of time to be saved in the actual G-code, so unnecessary lines, unnecessary accelerations, etc. And I want to try to dial in the combinations of accelerations and square corner velocities. I think there's a lot of speed to be gained. Build a proper 1 minute 59 G-code with the 0.4mm nozzle and then do the exact same brute force parameter finding for temperature, pressure advance, etc. and dial that in, and let's see how good of a quality Benchy we can print sub 2 minutes. That's it for tomorrow. Yeah, it's the next morning. I just went ahead and wanted to test some new G-code, and yeah, this is the result of me typing in 750% speed instead of 75. This did crash. Yeah, let me get all the like glass splinters, etc. from here, because they actually might scratch everything. Yeah. Be right back. Alright, so you may have seen me dry running some G-code. Let us get over this code and what I'm trying to accomplish with it, and then we're gonna run it. So this will be the 1 minute 59. Again, this is my goal, to be sub 2 minutes. And this has a lot of tricks from the book in it to improve quality. So this is what we're after. Just for comparison's sake, with these speeds and feeds I'm running and accelerations and square corner velocities, etc., we could go down to like 1 minute 40 if I use 0.5mm nozzle, etc., and get rid of unnecessary code. Let's try to do a quality sub 2 minute run, and this involves something like having very slow first layers, going down with outer wall speed. We're doing a lot in terms of overhangs, getting those down. We're using pretty much 650k accelerations and square corner velocities between 100, 125 for normal printing moves. And I don't even know if that makes a difference for travel moves, but it's set to 300 and it ran through. Modifiers for the top. The chimney part is running pretty slow. We added a modifier. Let's have a look here at the speeds tab. I've set a modifier for all the top surfaces. These are down in speed, and for this whole middle part here with the pillars, the layer time was so low in early attempts and we don't have any fighting chance of cooling that down. I pulled a lot of speed in this area. This is around 390, 400 millimeters per second. Then we also have some layer height decrease here at the top. This is going down to, I think, 1800th of a mil to give it a bit more chance to get these overhangs right. We do not combine infill layers. This is still 10% of line infill, but we do not combine because I want this to be solid infill, to have everything above a chance to actually adhere to something. In terms of flow, this is still 164 is the biggest number we hit with the nozzle. Yeah, we're paying that with adding a lot of speed in the rest of the Benchy. So all these outer walls, especially the infill part, is at 750 millimeters per second. This is just a baseline. Let me run that at 50%. That should come out to, I don't know, 3 minutes 15 again. Let's see how that looks and then dial up the speeds and see where we can improve. So this would have been 3 minutes 20. It ripped off the build plate somewhere here at that top section, but this is actually quite interesting because it is giving us some insights on what is happening here. And as you can see, this is the first speed Benchy that has crisp overhangs here. So going down with the speed, reducing the layer height seems to have made an advancement here. It ain't perfect on the back window, but yeah, it's still pretty okayish. Other sides also good. And then you can see here up front, the top part is actually pretty good. And all that stuff you can see beneath there is actually the first layer of bridging that goes on top of here. And you can basically see that all these lines basically stuck here. Then it went over there, it didn't catch the back lip, and it pulled the string back across here. We're running this at 250 millimeters a second. I guess this is just the air being still too hard on it to actually give it a fighting chance of pulling the string across here. So cooling wasn't turned all the way up. I wanted to see if I could get rid of this by going lower in cooling, but this isn't the case. I cranked it up there and it looks fine again. At the top you can see that we reached the limits of cooling with 75%. This, what has been crisp before, isn't anymore. Let's run 100. Alright, didn't make it to the end, and also you can see what happened here. I think with this material we reach the limit of what the current cooling is capable and also the extrusion. So running these walls at 1 meter a second, to compare that to 750 millimeters, that's looking way better. So I guess we shouldn't exceed that for the moment, at least with this kind of material here. But in order to run it sub 2 minutes, I have to go higher. I could crank up the accelerations even more, but we're coming to a point where I have to go to insane numbers to cut down a few seconds. And also you can see the square corner velocity. I'm gonna retighten those ropes now, but as you can see, the square corner velocity of over 100 millimeters is paying its toll by rounding off the edges quite a bit. But at least the system itself is running really consistently without losing steps. I'm also just running these at 2 amps. I could go to like 4 amps, but again, I don't want to risk melting anything. For my next test, the longer tubes that are facing right at the nozzle tip, I'm gonna block off these with some tape and just gonna run the shorter ones with 360 degree and see if that makes a positive difference in terms of not blowing the filament away, but keeping kind of the same volume flow. So as I said, I taped half of those outlets shut. This is the result. So in a few parts it does look better. In other parts it looks worse. I don't think this is where we find our solution. Let me take a break and think about what is here in front of me on the plate. Well, welcome to my proudest moment. You know how the saying goes? Fool me once, shame on you, and fool me twice, well... yeah, there's a little bit of carnage here. Yeah, so you remember the thing where I wanted to type in 75% and then accidentally fat-fingered A3 into that before I hit enter? Yeah, it happened again, but at least the upside is, this time we got it on tape. So yeah, I wanted to end this video with a bang, and I think that scripted itself. But I think this is a perfect opportunity to talk about prototyping, mechanical engineering, and the process behind all of these things. So I've mentioned it a number of times. This machine consists of so many untested parts and basically just theories on the extruder, the motion platform, the cooling, etc. I'm going new ways, and failing is a total naturally experience in that regard. And ultimately, the key to success is failing one time less than you actually started something. And you see me here pretty much raw cut in such a field. I'm doing all of this in my free time. I can't do this as my main job just now. There are setbacks, a lot of them. You probably haven't seen all of them, but you've been with me on the journey. And let's have a look at the journey. These aren't all of the prints the machine has done. These should be like 35 or something. We started and the numbers or times went down, down, down. This was the first attempts at 2 minutes. Then we dialed it back again a bit, 3-4 minutes, and then we got faster again. And you can see a progression through all of these prints. So this, for example, this is what I call the world record print. And if you just have a look at the last pieces we printed today, we made a whole lot of progress. What you've seen there and what you've seen today is by no means perfect. And to be honest, I never claimed it to be. So that's why I think this is a great opportunity to have a look at all the other guys and girls participating in this awesome challenge. So I'm not calling them competition or anything, it's like mutual masochists or something. Let's have a look at all the other entries in that area. So this is Monica McWuff's 1 minute 59 Benchy, the first to break the 2-minute barrier. And I think to this date this is still one of the best looking, and for this printer being a modified Ender 3, this is just spectacular. So I think we're gonna feature that in a future episode, so stay hyped on that. So then there is a 1 minute 53 Benchy by Kirapatka. I have tried to contact him multiple times to get a few photos of the finished print, but he never reached out to me. But yeah, this is also seems to be a modified Ender 3 chassis, and he's been also doing a quite good job at printing this. So Kirapatka, if you see this, leave something in the comments. I apologize for not having seen your time before. I didn't mention this in the comments. This has been like 1 minute 53 for at least a few months now. I never was aware of that video. And yeah, just lately there has been a 1 minute 50 run by the YouTubers named Kevin, which at first glance seems to be a German name, but it turns out to be a guy from Thailand. I contacted him via Discord, and he sent me a few of the pictures of that Benchy. And yeah, you can basically see that all of these people participating are having the 3 main limitations of physics basically in front of them. We have to move fast, we have to extrude enough material, and we have to somehow cool it. So looking at this footage and speaking with the people, I'm the only person who does have the extruder part at least solved in a way that there is enough material extruded. All of the others do suffer from mostly severe under-extrusion, sometimes up to 60%. It seems like pretty much all of them can run a sub 2 minute Benchy motion-wise. But I think especially on the Ender 3 machines, they are pretty much at their limits of what they can run. But basically, if you have a look at all of these approaches, all of them are stuck at cooling. There is just a brick layer I seem to encounter with air cooling, especially if you extrude 9.5 grams of material in sub 2 minutes. There is basically no way that air can cool this on its own. Even if we destroyed part of our current iteration of the machine, we gained so much experience during the process. If you just have a look at the Minuteman machine, motion-wise, we do have a lot of headroom. I'm still running the motors at 2 amps, and I can, like, if I cool them actively, I can run 6, 7, 8 amps or something like that. There is still lots of headroom. The hot end itself was designed to be working for the sub-minute Benchy, and we're extruding now at 150 cubes a second at 180 degrees, so there is so much headroom. I've proven that even with standard PLA you can extrude over 350 cubic millimeters a second, so that hot end is working like a charm. And also the extruders, again a shout out to the guys over at Bondtech with their LGX extruders. These things are just bonkers. All of this testing leads to the point we need to improve our cooling, and that's why the next episode will be solely about cooling. And we're gonna try a whole lot of stuff there. I already went ahead and built some really crude first prototype of a water vapor infusion into the cold airstream. The video about that I'll put here. And I've got a whole lot of other stuff planned, like running it with dry ice, running it with liquid nitrogen, using other type of gases, etc. For the end of the video, I would like you to do 3 things. First of all, please go back at the slow motion footage, and if you haven't at this point, type in everything you can read from that footage. It helps me for the long run iteration. Crowd intelligence here will make it way easier than just my 2 eyes. Second, I wanna have all your inputs regarding the topic of cooling. What are your ideas, what we can test in the upcoming videos, and how can we cool down our extrusion fast enough to actually run the sub 1 minute Benchy? And lastly, I'm gonna put a video of all the other guys and girls I mentioned down in the comment box. Maybe you're just gonna walk by, leave a like or something, so they get their appreciation too out of these videos. So, I hope you learned just as much as I did on this episode. My name is Jan, and I build stuff so you don't have to. See you next time. Bye. Like in the first video I said, we have to move fast, we have to extrude material